Hello viewers, my name is Dr. Ajay, Associate Professor, Department of ECE, Institute of Aeronautical Engineering College, Hyderabad. Today we are going to discuss the topic on a discussion of a tutorial question bank which relates to the course Antennas, Waves and Propagation. So let us have a small discussion of the tutorial question bank which belongs to the course Antennas, Waves and Propagation. It is this discussion is based upon the module 1 of the course AWP. Let us start our session. Explain the following terms: half power beamwidth, directivity, antenna efficiency. So explain the following terms: half power beamwidth between the first nulls, directivity and antenna efficiency. So the directivity of an antenna is defined as D is equal to the ratio of maximum radiation intensity of test antenna to the average radiation intensity of the test antenna. So here the directivity definition is denoted by symbol D, which is the ratio of pi max by pi AB. So pi represents the radiation intensity. The symbol of radiation intensity is pi. We can also represent it by the symbol U. So maximum radiation intensity we denote it by the symbol pi max or U max. Maximum radiation intensity of test antenna by average radiation intensity of test antenna. So directivity is equal to, we can denote it by the equation D is equal to pi max of by pi AB. So pi is a function of theta and pi. So pi, the radiation intensity is in three-dimensional plane. It will be continuously varying. When we propagate the signal into free space, it will be varied in the theta direction and also in the pi direction. In the theta direction and the pi direction. Hence, we are going to write the radiation intensity as a function of theta and pi. As a function of theta and pi. So theta comma pi of max by pi AB. So directivity can also be measured by taking a reference antenna which is known as isotropic antenna for the test antenna. So when we take the test antenna, when we take the isotropic antenna as a reference antenna for the test antenna, we can modify the expression as directivity is equal to maximum radiation intensity for subject antenna or test antenna to the radiation intensity of isotropic antenna. So whenever we are going to specify the isotropic antenna, we are going to denote it by the symbol pi naught. So pi naught represents the radiation intensity of an isotropic antenna. Similarly, G represents the gain of an antenna. G naught represents the gain with respect to the isotropic antenna. Gain with respect to the isotropic antenna. So if we want to measure the directivity in dB, we can use the equation D is equal to 10 log D base 10. 10 log D base 10. So the numerical value of D, directivity always lies between 1 and infinity. The numerical value of D always lies between 1 and infinity. Directivity will be always greater than or equal to 1. Directivity will be always be greater than or equal to 1 only. The next one is antenna efficiency. The antenna efficiency of an antenna is denoted by the symbol eta. So the power radiated to the total input power, it is known as the antenna efficiency. So the antenna efficiency depends upon the power radiation and the total input powers. How much amount of power is given applied to the transmitting antenna and how much amount of radiation is happening. How much amount of power is radiated. So here the total input power depends upon two factors. One is the input WT. It depends upon WR plus WL. So loss power and radiated power. So the total power is given by the formula radiated power, the summation of radiated power with respect to the loss power. We call it as the antenna efficiency. So WT. So the WT depends upon two components. One is the radiated power and the loss power. So the ratio of WR to the WT is known as the antenna efficiency, denoted by the symbol eta. And efficiency we can also define by another expression as the ratios of power gains. The power gain to the directive gain we call it as efficiency. The power gain to the directive gain is also known as antenna efficiency, which is denoted by the symbol GB by GD is equal to WR by WR plus WL. We can also use this antenna efficiency in terms of radiation resistance. So RR by RR plus RL. So efficiency as a measure of percentage, we can measure in terms of percentage as RR by RR plus RL. Why? Because W is equal to IR, W is equal to VI, V is equal to IR into I. This is equal to I square R. Simply we can write as I square RR, the radiation resistance. So antenna beam width. So antenna beam width, it is aperture angle where the most of the power is radiated. So beam width is aperture angle from where the most of the power is radiated. There are two beam width types of beam widths can be measured in the major lobe of the radiation pattern. So whenever we draw the radiation pattern, we are going to draw the radiation pattern in the far field only. So there are different types of lobes: major lobe, minor lobe, side lobes. So we can measure any parameter like gain, directivity, half power beam width, or effective length, or any parameter in the major lobe only into consideration. So when we take the major lobe here, this is the major lobe. So we take exactly mark 2 points exactly at a half of the major lobe. This is the major lobe. We mark exactly half points of the major lobe. The angle between half power points of the major lobe, we call it as half power beam width. So this is known as half power beam width. Mark 2 points exactly at a half of the major lobe. The angle that is taken exactly at a half of power of the major lobe, we call it as half power beam width. And these are known as the side lobes or minor lobes. And the angle between these two nulls, first nulls, these are known as first null. This is known as first null. The angle taken between these two first nulls, we call it as the half power beam width. We call it as the half power beam width. So I have shown the figure. The simple definition of half power beam width is the angular separation in which the magnitude of the radiation pattern decreases by 50% from the peak of the main beam is the half power beam width. First null beam width or beam width between the first nulls. The angular span between the first pattern nulls adjacent to the main lobe is called as the first null beam width or beam width between the first nulls. Generalize the relationship between the directivity and the beam solid angle. Generalize the relationship between the directivity and the beam solid angle. So we know that the directivity of any antenna depends upon the effective aperture of the antenna. We know that the directivity depends related to the equation of effective aperture. Why? Because D is equal to, we know that 4 pi by lambda square into AE. So here the directivity depends upon the effective aperture. Let us assume two antennas A and B. Let us assume DA as a directivity of antenna A and DB as a directivity of antenna B. Assume AE as effective aperture and AEA as effective aperture of antenna A and AEB as effective aperture of antenna B here. So based upon this terminology or based upon these specifications, so we can write as DA is proportional to AEA max and DB is proportional to AEB max. And from these two ratios, we can simplify as DA by DB is equal to AEA max by AEB max. So AEA max by AEB max here. Now we know that there is a relationship between the gain and the directivity, which is denoted by symbol G0. So gain with respect to the isotropic antenna is equal to G0 is equal to KD. So G0 is equal to KD. Let us assume the gain of the transmitting antenna A as GOA. The gain of the transmitting antenna B, it is known as GOB. And the effectiveness ratio is denoted by symbol alpha. The effectiveness ratio is nothing but the ratios of effective aperture to the maximum effective aperture. So alpha is known as the effectiveness ratio, the effective aperture of an antenna to the maximum effective aperture of that antenna. We call it as the effectiveness ratio alpha. Assume that the alpha, the effectiveness ratio of antenna A as alpha A, and for B we denote it by symbol alpha B. Assume alpha A, alpha B be the effectiveness ratios of A and B antennas. GOA and GOB be the gains of the isotropic antenna of transmitting antenna A and B. Now we know that there is a relationship G0 is equal to KD. So based upon this, we can modify G0 is equal to alpha D, the effectiveness ratio. And here, as specifications, we can write as GOA is equal to alpha A and DA. Similarly, GOB is equal to alpha B into DB here. Now let us find out these two ratios. Let us find out these two ratios. You will get as alpha A dA by alpha B dB. And here we know that the alpha is equal to the effectiveness ratio. It is the ratios of effective aperture to the maximum effective aperture, which is denoted by AEA by AEA max. So AEA is equal to alpha A into AEA max. AEB is equal to alpha B into AEB max. Let us substitute this alpha A value in this equation and alpha B in this equation. If you substitute and simplify, you will get GOA by GOB is equal to AEA max by alpha B into AEB max here. So if we simplify, you will get GOA by GOB is equal to AEA by AEB. Now let us assume the antenna A is isotropic. Let us assume that we have taken first two practical antennas A and B. Now let us assume this antenna A as the isotropic. The directivity of an isotropic antenna is 1. The directivity of an isotropic antenna A, it is assumed as 1 here. Putting this condition in equation 74, we know that dA by dB is equal to, we are having the equation in the equation 74 here. So dA by dB is equal to AEA max by AEB max. So the isotropic antenna is A, the directivity is 1. So we can substitute here as the directivity is equal to 1 here. Directivity is equal to 1. So 1 by dB is equal to, you will get AEA max by AEB max here. So from this equation, we will get AEA max equal to AEB max by dB here. So here the maximum effective aperture of transmitting antenna A is equal to the ratios of the maximum effective aperture of B to the directivity of the antenna B here. Now let us make some assumptions here. Let maximum effective aperture of short dipole antenna is 3 by 8 pi lambda whole square. 3 by 8 pi whole square here. And the directivity is 3 by 2. So here from this equation we can write here AEA max equal to AEB max. So here 3 lambda square by 8 pi here. And 3 lambda square by 8 pi into 2 by 3. 3 get cancelled, you will get 2 into 2 4 is equal to lambda square by 4 pi here. So this is 3 lambda square by 8 pi here. So let us assume the maximum effective aperture of the short dipole antenna, that is antenna B. Assume antenna B as the dipole antenna where the effective aperture is given as 3 lambda square by 8 pi and the directivity is 3 by 2. So under these two conditions, if we simplify, you will get lambda square by 4 pi. So AEA max equal to lambda square by 4 pi, or simply we can modify this equation as AE is equal to lambda square by 4 pi. So AE is equal to lambda square by 4 pi. So again we are having a relationship between the directivity and the effective aperture. So dB is equal to AEB max by AEA max. So here we can have here as AEA max equal to AEB max by dB, and just now we got the value of AEB max. We got the value of AEB max. It is AEA max as lambda square by 4 pi. Now let us substitute this value. By substituting this value, you will get the directivity is equal to 4 pi by lambda square into AEB max. So D is equal to, we can simply write as, generalize as 4 pi by lambda square into AE. So this is the relationship between the maximum effective aperture and the gain or directivity. So D is equal to 4 pi by lambda square into AEM. Now briefly explain about the effective length of the antenna. So an antenna in the receiving mode or the transmitting mode, whether it is in the form of a wire, horn, aperture, is used to capture electromagnetic waves and to extract power from them to radiate. So the effective length is denoted by symbol LEA. This is equal to open circuited voltage to the incident field strength. So it is given by the open circuited voltage to the incident field strength, which is given as LE is equal to V by A. LE is equal to V by E here. So if we simplify, LE is equal to V by E and the open circuited voltage by incident field strength. So the effective aperture, we know that for an antenna is written as, it depends upon the load resistance V square RL by RA plus RL whole square plus XA plus whole square into P. So we can also modify this V square is equal to AE into E square by Z. So P is equal to P can be replaced as E square by Z here. P is equal to V into I. And here I is equal to V by R here. So this is equal to V square by R here. So as we are going to calculate the average value of power, we cannot directly measure the voltage at a particular point. So we are going to measure in terms of impedance. That is, V can be modified as E square and R can be written as Z here. So P is replaced as E square by Z here. So P is replaced by E square by Z. So if we simplify, you will get V is equal to root of A square into RA plus RL whole square plus XL whole square. So under the conditions of maximum effective aperture, if we want to transmit maximum amount of power from one area to the other area, the reactance must be same. The reactance must be same with opposite polarities. So XA must be equal to minus XL, and the resistance of both the devices must be same. So the resistance components, whichever from the transmitting antenna and receiving antenna, must be equal, or the reactance components must be same with opposite polarities. Under these two conditions only, we can transmit a large amount of power between two devices or two stations. So L is equal to V by E. Substitute the value of V here, V by E, and we are going to simplify the conditions of maximum effective aperture by substituting these conditions in this equation. So if you simplify this, you will get AE max equal to LE square Z by 4RR. LE square Z by 4RR. So this is the condition we are going to calculate the maximum effective aperture in the receiving mode. So whenever you are going to, how much amount of field strength is received by the receiver depends upon the maximum effective aperture of the receiving antenna. So the maximum effective aperture of the receiving antenna is related to the equation LE square Z by 4RR. Similarly, in the transmitting antenna, we can write the effective length of transmitting antenna as 2 by I of C integration of 0 to L by 2 I of Z dz. So 2 by I of C integration of 0 to L by 2 I of Z dz. The reciprocity theorem. So state reciprocity theorem for antennas and show that the transmitting and receiving patterns of an antenna are equal. So antenna can be used both as a transmitting antenna and receiving antenna. The properties of antenna being unchangeable is called as property of reciprocity. And the statement of there are two statements of reciprocity theorem. The first one is, if an EMF is applied to the terminals of antenna number 1 and current is measured at the terminals of antenna number 2, then an equal current both in amplitude and phase will be obtained at the terminals. So if an EMF is applied to the terminals of antenna 1 and the current is measured at the terminals of antenna number 2, then equal current both in amplitude and phase will be obtained at the terminals of antenna number 1 if the same EMF is applied to terminals of antenna number 2. So according to the statement, suppose there are two networks here, two stations here. Suppose we are applying a EMF, this is 1 and this is 2, and we are going to calculate the current at 2, assume as I2. Suppose E1, we have applied EMF at antenna 1 and we are measuring I2 at antenna 2. And if we apply E2, if we apply the same EMF at 2 and measure the current I1, measure the current at the transmitting antenna 1 as I1, then I1 will be equal to I2, provided E1 is equal to E2. So if we apply the same EMFs, that is at 1 and 2 antennas, at the transmitting antenna, receiving antenna, then the currents will be measured will be same. That is, I1 will be equivalent to I2. So this is the statement of reciprocity theorem. So these are the equivalent circuit diagram of the reciprocity theorem. So here we are going to apply some EMF as E12. We are going to measure the I2 here. Similarly, we are going to apply E21 here. We are going to measure I1 here. So we need to prove that I1 is equal to I2, provided E12 is equal to E21. Provided E12 is equal to E21. So first we shall write for this the Kirchhoff's mesh law here. And for this also we'll try to write the Kirchhoff's mesh law, and we'll try to prove the I1 is equal to I2 provided E12 is equal to E21. So if we write the Kirchhoff's mesh law for this equation 1, we'll write as I2 is equal to I1 into, we can write as Z22 plus Zm into I2 minus Zm into I1 is equal to 0 here. Right? So for this equation, suppose this is Z11, this is Z22, this is Z12, the mutual transfer impedance, and here this is E12, and this is we're applying I2 here. So let us assume this as Zm, the mutual impedance. So for this equation, we can write the Kirchhoff's law as for loop 2 here, this is 2, this is 1. So here we can write this as, for this equation, let us write as Z11, this is Z22, and this is Zm, and this is I2 here. These are terminals 2 here. These are terminals 1, 1 dash, 2, 2 dash. We are applying here E12 at these two terminals, and this is one loop, this is second loop. So for the second loop, we can write the equation as the from loop 2, Z22 into I2, the current supply will be in this direction, and here I1 here, I2, this is I1. So Z22 I2 plus Zm I2 minus Zm I1 is equal to 0. So from this equation we can write simply as I2 is equal to I1 into Zm by Z22 plus Zm. Similarly for this equation also, for this loop 1 also, we can write Zm into I1 minus I2 plus Z11 I1 is equal to E12. So Zm into I1 minus I2 plus Z11 I1 is equal to E12. So this is the equation. Let us simplify this equation by substituting the value of I2 here. In the previous equation we got the I2 value here. Let us substitute this equation here and simplify. You will get I1 is equal to E12 into Z22 plus Zm by Z11 plus Z22 plus Zm into Z11 plus Z22. So for simply mathematical equations, if you simplify, you will get equation 4. So we got I1. Similarly, we shall take another network and we'll try to write the equation, find out the value of I2 here. Now for this case, we have applied I2 here. And similarly, let us apply I1 here. Let us apply I1 here. I'm going to measure here E21. Apply I1 here. This is 1 and this is 2. And here this is Z11 and this is Z22 and this is Zn. Clear? So for this equation also we are going to try to find the value of I2 here. Similarly, if we try simplify, you will get E12 into Z22 plus Zm into Zm. So I2 is equal to E12 into Zm by Z11 is Z22 plus Zm into Z11 plus Z22. So equations 4 and 5 will be equal only when the condition E12 is equal to E21. So we are going to give the same EMF at both the terminals of 1 and 2. Now equation 4 is equal to equation 5. Let's equate these two equations. If we equate these two equations, all these things get cancelled here. E12 into Z22 plus Zm. And you will get I1 is equal to I2. So provided phi is equal to 6. Hence the theorem is proved here. Demonstrate the Friis transmission formula here. So based upon the applications of reciprocity theorem, we can demonstrate the Friis transmission formula here. So from the equation, directivity is equal to maximum radiation intensity by average radiation intensity. So D is equal to pi max by pi AV, and pi AV is equal to W by 4 pi. So here D is equal to pi max by pi AV, and pi AV is equal to W by 4 pi. Substitute this AV value here. We will get pi max by 4 pi. 4 pi into pi max by W here. 4 pi into pi max by W here. So this we got here. So the directivity is equal to 4 pi by integration of pi n d omega. Now let us derive the Friis transmission formula. So we know that the power radiated by the isotropic antenna is Wt. Let us assume Wt as the power radiated by transmitting antenna. And the power received per unit area receiving antenna is given by P is equal to Wt by 4 pi r square. P is equal to Wt by 4 pi r square, where r is the distance between the transmitting antenna and receiving antenna. So the amount of power received or receiving antenna depends upon the power transmitted. So we have written the equation Wt by 4 pi r square. Also, the power received or receiver depends upon the effective aperture of the antenna. Depends upon the area. That is what is the area of the antenna. We call it as the effective aperture of the antenna. So we denote it by symbol W dash. So W dash is equal to AER into P. So if you substitute here, you will get WR dash is equal to AER into WT by 4 pi r square. So if we simplify this P value in this equation, so you will get WR dash is equal to AER into WT by 4 pi r square. So with this relationship between directivity and maximum effective aperture, so dt is equal to 4 pi by lambda square into AEMD. So the power received by the receiver is given by the total power received by the receiver depends upon the effective aperture of the area, the power received by the receiver, and the directivity given by the relation WR is equal to WR dash into dt. So WR dash into dt here. So dt is equal to, we know that 4 pi by lambda square into AEMD, we substitute here, and WR dash is equal to, we know that it depends upon WT by 4 pi r square. And let us find out the ratios of WR by WT. Ratios of WR by WT is equal to AER by r square into AEMD by lambda square. So this is known as the Friis transmission formula. So Friis transmission formula gives us the ratios of the power received to the power transmitted to the direct path. So these both ratios depends upon the effective apertures of the transmitting antenna and the effective apertures of the receiving antenna here. So the power received to the power transmitting antenna WR by WT is equal to AER AET by r square into lambda square. R represents the distance between the transmitting antenna and the receiving antenna. So to apply Friis transmission formula, this condition has to be satisfied. One is r is greater than 2d square by lambda. So d is the dimension of the antenna or the length of the antenna. We can also represent this Friis transmission formula in terms of gain. Why? Because we know that G is equal to KD here, and if K is equal to 1, the efficiency factor, then G naught is equal to D here. We know that D is equal to 4 pi by lambda square into AA. This is equivalent to G here. So for this, we can write as GT for transmitting antenna, GT is equal to DT. And similarly, we can have for directive receiving antenna is equal to, this is AET. This is for 4 pi by lambda square AER, this is equivalent to GR. So GT is equal to DT and GR is equal to DR. So 4 pi by lambda square into AET, 4 pi by lambda square into AER. So we can substitute these two equations, further simplify. So you will get WR by WT is equal to GT GR by 4 pi r by lambda whole square, where lambda by 4 pi r whole square is known as a free space loss factor. We call it as a free space loss factor. So we are having two equations for Friis transmission formula. One is in terms of effective aperture, the other one is in terms of gains of the antenna. So WR by WT is equal to AER AET by lambda by 4 pi r whole square. Or we can also describe as WR by WT is equal to GT GR into 4 pi r by lambda whole square. So the next one is demonstrate the way in which an oscillating dipole throws out its radiation. So whenever we are going to apply some amount of current here for a dipole antenna, a dipole is nothing but it's a small conductor which is having same amplitude or same magnitude at both the ends, but with the opposite polarities. So when we apply a small amount of current here, exactly the center of the conductor, the charges start moving here. So whenever these charges start moving here, some amount of radiation here. So time t is equal to 0. Whenever we apply the high frequency current, electromagnetic ray will be in this direction. So after some time duration of t is equal to 1 by t, these positive charges, which is at the end here, will move at the distance of here, and these negative charges, which is at the distance of at the end point, move at this point. So the path will be like this. So after some time interval, when these oscillations of charges is happening, when these charges start moving, here the path, the electromagnetic wave path will be like this. So at time t is equal to 3 by 8 of t, the plus charge which is at the one end point, it will move to the another end, and the negative point or the negative charge which is at this end will move to the other end. Hence, one electromagnetic ray path will be detached from the conductor at 3 by 8 of t. So like this, as the speed of the charges or the oscillation of charges increase, the radiation of electromagnetic paths will be detached. More number of electromagnetic paths will be detached from the conductor and will be escaped into the free space. Hence, these are known as this is how the radiation is thrown out from the oscillating dipole antenna. So antenna operating at a wavelength of 2.5 meters has a directivity of 90. So determine the maximum effective aperture. We know that the AEM is equal to lambda square by 4.2t. The wavelength is given as 2.5 meters directly. Substitute the value of d here, 90. So if we substitute here, we will simplify 44.76 meters here. So microwave link is to be designed such that transmitting and receiving antennas are separated by distance of 30 miles. So the distance is given as 30. Directive gains is given as GT is equal to GR is equal to 45. This is given in dB, so we need to convert into decimal here. And the frequency is given as 3 gigahertz. And the power received PR is equal to 1 into 10 power minus 3 watts here. And the separation of distance is given as R is equal to 30 miles. So we need to find out the power transmitted. So we are going to apply the Friis transmission formula, where the ratios of power received to the power transmitted depends upon the gains. So GT GR by 4 pi r by lambda whole square. So just we are going to use the formula WR by WT is equal to GT GR by 4 pi r by lambda whole square. So R is given as 30 and lambda depends upon the value of F, that is 3 gigahertz given. So C is equal to F by lambda. We substitute here lambda is equal to C by F. So C is equal to 3 into 10 power 8 by F is equal to 3 into 10 power 9. And similarly GT and GR is given as 45 dB. And WR, the power received, it is given as 10 power minus 3. It is 10 power minus 3 watts. So from this equation we need to find the value of WT here. So F is equal to 3 gigahertz given, C is equal to F by lambda, or C is equal to F lambda. And from this equation, lambda is equal to C by F. We need to find out. So here, so these are the data given. We need to convert the 45 dB in decimal value, 10 log 45. We'll get 31.6 in 10 power 3. And substitute all these formula values in the formula. So you will get the value of power received here. So antenna has a radiation resistance of 73 ohms and loss resistance of 7 ohms. So if the power gain is 20, calculate the directivity and efficiency of the antenna. So we are having efficiency is equal to RR by RR plus RL formula. So from this we can find out the efficiency value here. We'll get 0.9. And the power gain is given as 12 dB. So we are having relationship GP is equal to eta GT. Substitute this efficiency in this value, and we need to find out the directivity. So directivity is denoted by the symbol GD here. So GD is equal to we are getting 15.8 by 0.9 is equal to 12.45 dB. So for all these question bank questions for module 1, you can refer the John D. Cross textbook, Antennas Wave Propagation by Bakshi, and also K.D. Prasad, that is Antennas Waves and Propagation. So let us close the session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.